Imagine a computer so powerful that it could help discover life-saving drugs, revolutionize artificial intelligence, or even rewrite the rules of internet security. This isn't the stuff of science fiction, it's the promise of quantum computing. Often called the next technological revolution, quantum computing has the potential to transform science, technology, and society in ways that we're only just beginning to grasp. But what makes quantum computing so unique? How close are we to its realization, and what challenges lie ahead? Today, we're going to explore how this groundbreaking technology could forever change human life. What makes quantum computing different from the classical computers we use every day? Think of how computers traditionally work, using bits that are either a 0 or a 1. From your smartphone to the world's most powerful supercomputers, every piece of data and every calculation boils down to these binary states. Quantum computing throws that simplicity out the window. Instead of bits, quantum computers use qubits, and these qubits can do something wild. They can exist in a state called superposition, where they're both 0 and 1 at the same time. This isn't just a quirky property, it's a game changer. Imagine trying to solve a maze by walking down one path at a time. That's how classical computers approach problems. But a quantum computer? It's like sending 1,000 explorers down every possible path simultaneously. The result? Certain types of problems that could take modern supercomputers millions of years might be solved by quantum computers in hours or even minutes. Then there's entanglement. When qubits become entangled, the state of one qubit directly correlates with the state of another, even if they're physically far apart. This allows quantum computers to perform coordinated computations at an unprecedented scale. It's as if pieces of the puzzle are solving themselves together, even if they're on opposite sides of the room. Finally, there's quantum interference. By controlling the wave-like nature of qubits, quantum computers can amplify correct solutions and cancel out wrong ones. It's like creating a shortcut to the most likely answer, nudging probabilities into your favor. These concepts give quantum computers their enormous potential. But let's bring this back to Earth. What could quantum computing mean for our lives in the near future? In the short term, one of the most exciting applications is quantum simulation. The natural world, chemistry, biology, physics, operates according to the rules of quantum mechanics. Classical computers struggle to model these complex systems because they simply don't speak the same language. Quantum computers, however, are built to mimic quantum systems, meaning they could crack problems like simulating molecular interactions much faster. This has groundbreaking implications. For instance, in drug discovery, researchers could model how a new medication interacts with the human body at the molecular level, drastically cutting down the time and cost it takes to bring life-saving treatments to market. In materials science, we might discover new superconductors that could revolutionize energy grids or design ultra-efficient batteries to power the next generation of electric vehicles. Next, let's talk about optimization. Quantum algorithms are particularly good at solving optimization problems, things like finding the shortest route for delivery trucks or maximizing the performance of large-scale financial portfolios. Companies in sectors like logistics, finance, and manufacturing stand to gain massively as these algorithms mature. And then there's security. You've probably heard that quantum computing could break the internet by cracking widely used encryption methods. Here's how. Many encryption systems rely on the difficulty of factoring large numbers, a problem classical computers struggle with, but quantum algorithms, like Shor's algorithm, could solve in an instant. But quantum computing isn't just a threat to security, it's also a solution. Quantum key distribution, or QKD, creates communication channels so secure that any attempt to eavesdrop would be immediately detected. Within the next decade, we may see quantum-secured networks becoming a part of our daily lives. Of course, this is just the tip of the iceberg. The long-term vision for quantum computing is even more transformative. Let's talk big picture. For one, quantum computers could solve problems that are fundamentally intractable for classical machines. Consider the mysteries of the universe, how stars are formed, how black holes behave, or even the fundamental nature of reality itself. By simulating quantum systems, we might unlock answers to questions that have stumped scientists for centuries. And it's not just about deep space physics. Quantum computing could drive revolutions right here on Earth. Imagine precision drug therapies tailored to an individual's unique genetic code. Picture ultra-efficient solar cells and materials engineered atom by atom to combat climate change. These aren't just possibilities, they're problems quantum computers are uniquely suited to tackle. In the field of artificial intelligence, quantum machine learning is another emerging frontier. Our current AI systems are limited by the scale of data and the complexity of algorithms they can process. Quantum computing could power AI capable of handling far more sophisticated tasks, unlocking new realms of creativity and insight in everything from art to medicine. But with great power comes great responsibility. Just like the digital revolution brought us both social media and cybercrime, the rise of quantum computing will have its share of challenges. So, what's standing in the way of this quantum future? For one, there's the hardware. Building a functional quantum computer is like trying to trap lightning in a bottle. Qubits are incredibly fragile and prone to errors caused by even the slightest interference, like heat or radiation. To make a single reliable, logical qubit, we often need thousands of physical qubits, and maintaining that kind of stability is enormously difficult. This is where quantum error correction comes in. It's a field unto itself, requiring ingenious methods to reduce noise and prevent computation errors. Some experts believe we'll need millions of high-quality qubits to build a truly fault-tolerant quantum computer, an engineering challenge on an unprecedented scale. Then there's the software. Designing quantum algorithms isn't as simple as writing code for a classical machine. Many problems we face today might not even lend themselves to quantum solutions, and finding real-world applications where quantum computers truly outperform classical ones is still an active area of research. And we can't ignore the ethical considerations. Quantum computing raises serious questions about privacy, security, and fairness. If only a handful of governments or corporations control the most powerful quantum machines, does that centralize power in dangerous ways? Will quantum breakthroughs be shared equitably, or will they deepen existing disparities between nations and industries? And yet, despite these challenges, the promise of quantum computing is undeniable. It's not just about faster processors or better encryption. Quantum computing forces us to rethink what we mean by computation. It blurs the lines between science, philosophy, and technology, tackling some of the most fundamental questions about the universe. Will quantum computing live up to the hype? Only time will tell. But one thing is certain, we're on the brink of a new era of discovery, one where the limits of what's possible are continually redefined. Just as fire, electricity, and the transistor transformed human civilization, quantum computing may well be the next great leap forward. So keep your eyes on the horizon, because the quantum revolution is only getting started.